Hello, and welcome back to this course on causality for psychologists and social scientists. Welcome to week 5, which is machine learning basics. Before I get into the basics, I wanted to revisit this network of techniques, which hopefully convince you that triangulation is an important and useful part of the research process, so that we don't just take one approach to research, but rather we combine lots of different approaches. And I thought it would be interesting to see where machine learning can fit into these different areas. And certainly in prediction, we see machine learning being used a lot. And this can also help us at the exploratory stages of research to identify useful predictors for that task. So we run a prediction task, we might have a list of predictors, and we want to identify which ones are most predictive of some outcome. We'll talk about that more later on. And to that extent, I've got this sort of bidirectional arrow here from proto theory and prediction. So it might be our proto theory helps us decide which variables to explore in terms of predictive validity, but equally, we might discover new variables which suggest we maybe missed something out from our proto theory as well. That being said, this is a sort of unidirectional arrow from theory to prediction, because it's actually not clear, at least to me, how we might use prediction to strongly inform a theory, in contrast, with the proto theory, because if our theory is already sort of well formalized and mathematical, actually we'll come to see that prediction is quite limited in what we can do with it when it comes to actually informing the underlying structure behind a particular phenomenon. In contrast, and as we've already seen in the causal discovery lecture, machine learning is actually used quite a lot there. There are algorithmic approaches to discovering structure, and many of which we didn't mention at all, but there are many methods for causal discovery which seem to be gaining in popularity in the machine learning field in terms of a domain of research. We're going to use machine learning for causal inference in a later lecture. And so certainly, even though it's not so common right now, I think that's changing, and we're seeing a lot more causal inference methods in the top conferences in machine learning now. And so we're going to focus certainly on machine learning for causal inference. Okay, so with that, let's talk about prediction overall and also causality overall before we get into the basics. Just to set the scene. So prediction is obviously a very important task across many different disciplines, at least insofar as it's relevant to social science. We might, for instance, want to automate coding. So human coding in particular is a very expensive and time-consuming process whereby you train human coders to rate certain behaviors. Maybe they're watching a video back and they have to code certain behaviors and say, yes, this person displayed empathy or not in a certain segment. And they go through each second of this video coding the behaviors. And obviously this is very time consuming and, as I said, very expensive. And so if we can automate that process, that would obviously save a lot of time, and it would enable us to scale coding to much bigger data sets, much larger data sets with many more videos, and do so in a relatively low cost and automatic way. We can also automate decision processes, and indeed this is one of the functions of machine learning that's very popular in industry, to speed up certain relatively straightforward processes just by automating them. And indeed we can use similar processes for maybe automating assessment before therapy, making predictions of outcomes, trying to give us a sort of overall assessment of someone's state of mind or mental health. As I mentioned actually earlier, we can use machine learning in a predictive sense to identify predictive variables. And there was a paper recently that's certainly seems to be quite well regarded and quite well known by Samantha Joel et al. That looked at relationship-related variables and which variables were important across many different data sets. We also might want to use machine learning to investigate the predictive validity of theory. The idea being is if our theory is correct and it's a useful theory, then it should be able to help us also predict things. And if it doesn't, then maybe there's something not quite right about our theory. So there's a paper by Yarkoni and Westphal that I highly recommend. And we can also just simply explore the data for signal. And we'll be talking a little bit about, once we've done something, done a predictive task, we might be able to explain the machine learning model using machine learning explainability techniques, which is also part of sort of an exploratory technique to sort of identify useful variables and how they may or may not relate to others. But for the most part, these tasks have utility. but then they're only really indirectly related to the theory building itself. And so there's a limited sense by which we could use the results of these sorts of applications of machine learning for prediction to inform our theory. And even though we might be able to do some exploratory work that might help us, for instance, improve our proto theory, it's not particularly clear to me how we might use that to inform the mathematical model itself. The assumption being that maybe if we're already at the stage where we've got a theory that's well mathematically validated, there's a question as to whether or not exploring the data for other variables is a particularly good idea without necessarily revisiting the proto theory to really go back sort of a few steps to make sure we're building on reasonably firm foundations. I want to mention a caveat. This comes up a lot when I work with people in the applied fields like psychology, and my machine learning model seems to be working in a sort of reverse causal direction. And it's worth noting that at least non-generative machine learning, and we'll see an example of generative machine learning in a minute, most machine learning to that extent for prediction is anti-causal, to the extent that the outcome that we're trying to predict is often actually the cause in a process. And so just as an example, if the real world generative process looks like this, just for the sake of example, imagine I want to write a number. I may first consider the image class that I wish to write, say the number 8, and I have some kind of conception of what that digit is in my mind. This is arguably a latent sort of concept that determines how I move my pen on the paper. And so I may then, realize or manifest this 8 visually in pen and ink on paper as an 8 here. But there are many, arguably an infinite number of ways in which I could realize this 8 on paper. I could draw it, ever so slightly differently each time. In fact, drawing it twice the same way would be very difficult. And so whilst there's sort of one concept of 8 in this case, there are many possible realizations of it. So the causal direction is kind of from the digit class, which is very simple, to the image that I represent the class with. And so if I want to actually predict this 8, I would go the other way around. I'd use the image, which is lots of data. If it's in pixel form, I've got sort of, if it's just black and white, I would have 1s and 0s for every single pixel. And I'd be using those data to try and predict the image class. And this is indeed the application of handwritten digit recognition. But that's kind of like an anti-causal direction, because I'm using the realization, i.e. the effect, to predict the cause. And similarly, in a more sort of psychologically relevant example, my emotion, my arousal, and my valence may in turn sort of determine how I behave in terms of certain behavioral cues like verbal behaviors, non-verbal behaviors, paraverbal behaviors, how I move my hands, the way I speak, what I say, and so on. And yet, quite often in machine learning, we might want to, for instance, use the behavior which is observed to predict this sort of latent concept, emotion, and which is again sort of in an anti-causal direction. So, for instance, on the right-hand side here, I have the directions that we'd be using in machine learning. We'd be using the image to predict the image class, or be using the behavior to predict the underlying emotion. So something to watch out for. It doesn't mean that the machine learning model is wrong. It's just, in fact, the other direction is often sort of ill-posed or underspecified, because it's very hard to say to predict which image or which realization of the 8 I would manifest given a single image class. So given one 8, there are many possible solutions that would fit that 8. So it's a harder task in general. And if we just want to sort of classify the digit, we're kind of classifying the relatively low dimensional latent cause of that image. And in contrast, for generative models, and to give you an example of for instance, DALL-E 2 in action, in fact, let me just make sure I'm sharing the right screen here. So if I log into this is a generative model that you can sign up for and get access to. And it allows you to provide a text prompt, and it will generate an image in response to that text prompt. So for instance, an image of someone, in fact, let me say a photograph of someone learning about causality from animals. And so this is arguably more in the causal direction, because These concepts are relatively sort of discrete and low in terms of their dimensionality, arguably. And if you contrast that with the possible realizations of a photograph that corresponds with this, there are many possible solutions. So here are the images that it provides me. I guess it's tried to spell causality there. And this is the person, I guess, learning about causality. So arguably, this is sort of more in the causal direction in terms of a generative model. I guess in most cases, people aren't necessarily interested in generative models in psychology. Let me make sure I'm showing the right thing here. Yeah, that works. So it's kind of causal. I mean, the extent to which it doesn't provide me a detailed causal model of what's going on is maybe a separate point, but it is nonetheless more causal than the sort of general machine learning approach of using certainly the effect to predict the cause. So in which direction you're using depends a lot on your application. In general, I think that when you're using machine learning for prediction, you're probably going to be using the anti-causal direction. And to sort of decide which way around, you might consider things like, is the problem ill-posed in one direction but not the other? You know, for one digit class, are there possibly infinite number of realizations of that digit class, in which case you might want to go the other way around. Is the outcome one-dimensional, but the predictors high-dimensional? So in the case of the image, you know, we have an image with lots of pixels, say 728 pixels, and we want to predict one digit class is sort of, you know, again, about this sort of ill-posed nature of the problem. Are you developing a generative model, and are you definitely doing prediction rather than causal inference? So even in the predictive sense, you know, it doesn't really matter whether we're doing it anti-causally or causally. You're trying to just identify statistical associations that are useful for mapping from one space, i.e. the predictor space, to another space, i.e. the outcome space. And really, the causal direction doesn't really matter there. So in terms of causal inference, in contrast with prediction, the idea is that we do need to respect the underlying structure in the same way that we do linear models. We want to use machine learning in order to avoid linear models because of their unrealistic assumptions regarding the parametric form, like the Gaussianity of the errors, or the linearity of the functions. And when we use machine learning, we can therefore get better estimation, we hope, of the causal quantities that we actually care about. So these are arguably less biased because we're not sort of using a straight line to fit an otherwise nonlinear function. We need to think a little bit carefully about how to do statistical inference with the results, because machine learning is generally non-parametric, so we don't get automatically these confidence intervals, standard errors, p-values, and so on. And that will be one of the separate lectures. But otherwise, you know, what we're trying to do with machine learning is effectively model these functions. And indeed, our directed acyclic graph, as I mentioned before, sort of entails an underlying structural causal model with which is relatively agnostic to the underlying functions. So fx, fm, and fy here are three functions which could be arbitrarily nonlinear. And just to sort of motivate why a consideration for nonlinearity is useful, I first want to mention something about correlation. I think it's generally underappreciated that correlation itself doesn't follow a particularly linear behavior as you increase statistical dependence. So if we compare, for instance, a correlation of 0 here, these are all the same scale, all these graphs are the same x and y scale. We have this graph here, which is 0 correlation, Pearson correlation of 0. And then we increase that by 0.2. So this is a Pearson correlation of 0.2. And actually visually, there's not much change. So these are still very noisy. There's still a lot of variation between individuals in this data set, if you know, these represent variables pertaining to humans. But in contrast, you know, if we go from, say, a Pearson correlation of 0.8 to a Pearson correlation of 0.95, which is only an increase of 0.15 as opposed to here, which is an increase of 0.2, you see actually quite a marked difference between the two visually. And so it's worth noting that because correlation is going to asymptote at 1, it can't get higher than 1, it's just going to be a straight line at 1, you get this sort of nonlinear behavior where, you know, a relatively otherwise linear increase in statistical correlation doesn't really correspond with an increase that's sort of linear in correlation. So that's first thing to note. It's a bit of a by the way, but it maybe leads us on nicely to consider alternatives like mutual information, which behaves sort of maybe more intuitively. As statistical dependence increases, the mutual information increases along with it in a much more sort of linear fashion. To then move on to sort of what happens if we're just considering correlation in the face of nonlinearity, I created these here. This is a sine wave. This is a quadratic function. This is a toroid or a circle. And here we just have 4 Gaussian blobs. And what we can see is that, even though there's a strong information exchange or strong sort of information dependence between X and Y here, if I know something about X, I certainly know something about Y, the correlation is 0 because it essentially fits a straight line straight through the middle here. Similarly here, you also get a straight line through the middle. So even though there's a strong statistical dependence between X and Y, your correlation just gives you a 0 value. Same here, 0 value, and same here, 0 value. In fact, in the last instance, this last graph should be 0 because knowing something about X, knowing some information about X, tells us nothing about Y. So if we have the value X of 2, X equals 2, we don't know whether that corresponds with a low value of Y or a high value of Y. So it doesn't help us there. The correlation is actually 0 there. And you can see that mutual information here is also 0. And in contrast here, mutual information is 1, 0.783 here, and 0.402. In fact, the mutual information is a bit difficult because it doesn't range from -1 to 1. It sort of ranges from 0 upwards, unbounded. It depends on the entropy of the distribution. But the point here is really to make it clear that, even though we can see this strong dependence here between these variables, the correlation doesn't help us establish what that dependence is. So correlation itself is quite limited. There is a solution to this, which is that we could generate new features of the data. So in this one, it's particularly clear that this is a quadratic. And so if we just introduced into our data set not X as a predictor of Y, but X to the power of 2, as a predictor of Y, we would then be able to model the correlation linearly. But you're sort of just pushing the problem a bit further back at that stage, because even though we can create this variable and it looks well, it looks like it fits the data well, what if it isn't quite exactly X squared? We're kind of looking at these data and we're saying, yeah, an X squared looks about right. We could even fit an X squared model and see how it looks and measure the errors. But maybe it's slightly not quite an X squared. So you have to sort of try these other orders of polynomials, maybe 2.1, and maybe it's not just one polynomial, but it's a combination of other functions. So what I would argue is that really, in these situations where we're not sure, we can leverage machine learning techniques in order to approximate this complicated function, and to do so, and machine learning can do so in a way that's much more effective than we can. Obviously, then the challenge is to not overfit the data, and I'll talk about that in a minute. So to further motivate machine learning in the context of nonlinear functions and causal inference, these two graphs here are worth considering. So along the x-axis for both these graphs, we have sort of a percent or degree of nonlinearity in a function. And along the y-axis of the first graph is the error in the model. So how well we can fit the data using a particular model. The purple line at the bottom is the true model. So clearly, if we use the true model, the error stays at 0 no matter how much nonlinearity is there, because it is the true model. If we look at the red line, which is a logistic regression, you can consider that to be sort of linear for the purposes of this, and it is a linear model. You can see that when the percent nonlinearity is 0, the logistic regression also has an error of 0. In fact, that's because it is the true model at that stage. If there's no nonlinearity, and we're arguing that the data generating process for this is a linear model, then indeed the logistic regression fits that model perfectly, fits the data perfectly. But as we increase the nonlinearity, you can see the error of this linear model increases relatively monotonically along with the nonlinearity. In contrast, if we use a gradient boosting machine, which is a type of machine learning algorithm, you can see it's actually quite agnostic to the level of nonlinearity. It sort of doesn't really care how much nonlinearity there is, at least there's not this particular type of nonlinearity, and as such, it sort of maintains the same low error across the full sort of spectrum of nonlinearity. In a similar vein, this second graph here tells us how important a certain variable is, even when it's irrelevant. So we create the same data, but we have one variable in that model that is not at all related to the outcome. And then we look to see what the importance is that's being assigned to that variable. So in terms of the true contribution along the y-axis here, as we increase the nonlinearity, remains 0 for the whole spectrum of nonlinearity, which is the truth. If we use a gradient boosting machine, and here we also need some kind of model explainability technique to understand how important a particular variable is, we also get 0, which is really good. So it doesn't matter how much of this nonlinearity we introduce, the importance assigned to a particular variable in that model remains 0. In contrast, in logistic regression, the importance assigned to a variable, as judged, for instance, by the coefficient on that variable, increases linearly, in fact, with the nonlinearity of the model. So this is a bad thing, because even though the feature is irrelevant and it has no relationship to the outcome, the beta coefficient on that variable increases linearly as we increase the nonlinearity. So even though nothing's changed about the statistical relationship between X and Y here, just because there's a nonlinear relationship, the solution ends up assigning importance to variables that are otherwise irrelevant for the prediction. So that can be very misleading. So I hope that sort of motivates the consideration, at least for nonlinear methods or data adaptive methods, when we don't know exactly what the function is, how we're going to deal with that. And so that brings us on to the solution to that problem, which is, in this case, machine learning, which does open up other challenges that we'll talk about. For this course, I want to really be agnostic to the algorithm itself. So I'm not going to go into detail about how, say, support vector machines work, how random forests work, decision trees, and so on. There are many courses that are very good at doing that, and I don't think it really helps you understand the fundamentals, even though it's useful information for those particular methods. So I'm going to sort of consider, for the most part, I'm going to consider machine learning to be, for the most part, a black box into which we pass some data, some predictors X, and out of which we get some predictions, say Y hat here. And this function is supposed to sort of approximate the expected value of Y given X. And here is that expectation notation again. It's nice and general. It doesn't tell us what that function is. It puts some sort of theoretical constraints on the type of functions, but otherwise it's quite general. And so if the true process is some arbitrary function of X, we're going to try and approximate that function with F hat, and this algorithm is going to give us that F hat. And so these different techniques are sort of different ways to learn from the data, to compare what we predict from a given input against the truth for what that prediction should be, and we're going to modify F to become better and better at making those predictions. And so there are a long list of hundreds of different types of algorithms. People are always coming up with new variants and new algorithms in machine learning. They're all, there's a wide selection that are very powerful now, can let the data speak, as it were, to use Mark van der Laan's words. And there's a lot of example tasks: classification, regression, clustering if it's an unsupervised task. It might look a little bit different to this setup that we've given here. Representation learning, and at the bottom we've got causal inference. So we're going to focus on causal inference, particularly with regression models that are sort of approximating this expectation function. In terms of code, I want to convince you that actually implementing a machine learning model is very easy. And I think some people who've never done machine learning maybe have a misapprehension that to do so, you have to be very sort of mathematically sophisticated and knowledgeable. How on earth would I implement the random forest algorithm and so on? Well, you don't have to, because people have done it for you. And actually, if you want to go from a linear model here to a random forest, everything's the same. Outcome till the predictors data equals data, outcome predictors data equals data, data equals data. The only thing that we swap out is actually the function. Instead of LM, we now have random forest, which comes from the library random forest. And the same thing in Python. Things are really just a straight swap out, really. Some minor differences. So it's very easy to use machine learning. It's very hard to use it well, I would argue. And I think that's why, you don't have to, you get a lot of people that are using machine learning, and that's kind of good for the progress in the field, but it's also dangerous because people don't really understand necessarily what they're doing or what considerations they need to make to use it well and productively. And so I hope I can sort of shed some light on what some of those considerations are. Firstly, we're going to talk about overfitting and how we can do train-test splitting. In particular, this diagram here, we have some data points that follow this sort of sinusoidal curve, and we have some data points that are sort of off that curve. Maybe these are just noise, maybe they're outliers, but clearly they're sort of, I say clearly, we assume that they are not part of the original function that maps X to Y, but they are sort of some additional noise. And these green and blue lines represent the functions that are learned by two different types of decision tree. In fact, they're both decision trees, but one of them has a maximum depth of 2 and the other one has a maximum depth of 5. And these are what are known as hyperparameters. They're sort of settings that dictate how that algorithm can behave. And in this case, it's about making a decision. It's really a logical statement where we say, well, if X is above a certain value, predict Y for Y. If X is below a certain value, predict a different value of Y. And really that is the process here. You could represent the decision tree as a set of logical statements to say, well, between these two values, the output should be some value. And you can kind of see this with the blue line. First of all, you can see the blue line is predicting the function to sort of be a straight line here. So it will predict the same values for the target in this sort of region of the input space between 0 and say 0.4, for instance. And then what it does is for values of X greater than 0.4, it predicts this value of say 0.7 here. And it predicts it all the way across this range up to an X value of say 3. And then it changes and so on and so on. So it builds up this logical set of statements that tells you how to sort of carve up this input-output space to make predictions. And you can see in the blue case, it's a sort of very blunt way to make predictions. It's sort of saying, well, for the most part, all the way across this region, I can just predict the same value of Y. On average, that sort of works. It's not really captured the nice smooth curve of this function though. And even worse than that is what happens if we go even further with that, if we allow it to be more flexible. So max depth means that it can make more decisions for a given input space. Here we see this green line is starting to fit these noise points. So they're not really anything to do at all with the underlying sinusoidal function. But in order to minimize the error, in order to at least do well in terms of its goal of predicting the outcome, given the input, it started to fit very specific values. And the trouble with this is that if I show it some new values, it will maybe predict this low value here, even when what I want it to do is predict the value in there following this line here. So what happens with machine learning is that if you show it some data and let it fit those data, it will try to do the best that it possibly can on those data. And in so doing, it can often go beyond learning an expectation for Y given X. And it's to the point where it starts learning the actual noise itself. It can't disentangle the noise from the actual function. So here, this green function is sort of a pretty weird function. And that's its attempt, the algorithm's attempt at learning this expectation of Y given X. So we need ways to sort of pick good machine learning algorithms and make sure that they're not overfitting, but equally make sure they're not underfitting. For instance, this blue line here is also not great. It's not fitting the noise in the same way the green function is, but nonetheless, it's still sort of highly biased. It's not really doing a good job of learning the underlying function. And so just as a reminder, this is the goal. We want to learn the expectation of Y given X. For a particular value of X, there are multiple possible values of Y, and that comes as a result of the added noise. And so what we want to do is sort of pick a value in the middle of that noise, maybe the expected value of Y, i.e. the average value of all the possible noise values of Y around a particular X. And that should give us this nice smooth curve through the middle. And the hope is that this nice smooth curve is the actual underlying true function that represents the expected value of Y given X. And just some terminology then, if we say have this true function that follows this nice smooth line here, and we actually manage to achieve that, we might say that we've got optimal fit. Our algorithm has given us the best approximation to the true function. It's done a very good job of it. In contrast, if I fit a linear model, I might get this straight line here. And to that extent, we would say that it's highly biased. It's not fitting the data. It's not varying according to the input data. It's really just sort of a fixed line, and we've got high bias there. And so you can have anything in between optimal fit and high bias, but you can also go the other way, and you can say, well, what happens if I start to fit the noise like we saw with that green decision tree function on a couple of slides before? And indeed, that's sort of more what this wiggly line is here. It's high variance, it varies a lot, and in fact, it's too high variance. It started to fit the noise rather than the function. So some terms there, if we have high bias, we're kind of underfitting the data. And if we've got high variance, we might be overfitting the data. And then in the middle, we have this optimal fit. So our goal is really to find this optimal fit curve. And that will also help us predict new data. So when we get in new data that we haven't seen, we don't want to just predict anything. We want to predict something that follows the underlying function really well. And one of the problems, say, with this high variance curve here is that if I get new data in this range, it'll predict the outcomes to be sort of down here, when actually then, they're still following the optimal fit function. So that brings me on to two other terms. One is the interpolation range. So you can have new data either within the same sort of range or support of the original training data that you use to actually fit the original algorithm, in which case those new points will sort of fall somewhere around the old points. The distribution will look very similar. But then you also have this extrapolation range where you're looking at predicting data that really doesn't look like the data that you trained on. So you're almost generalizing to a new distribution here. So extrapolation is extremely difficult. You could imagine if you fit a really nice, say, cubic spline to some data, and it fits really nicely on the data that you fit it to, but then you get new data outside of that range. At least with a cubic, you might end up predicting sort of values near infinity because the polynomial sort of shoots off at either tail. So it's really difficult to get good functions that sort of can not only fit to the data that you have, but also generalize well on data outside of the original sort of range of your data sets. So one thing to bear in mind is to have a bit of a separation in your minds between prediction and estimation. And I've already talked about the differences between the two, but I also want you to consider how you use those two different tasks to pick your approach. So prediction is usually concerned with leveraging any and all correlations to predict something with high accuracy. So we task our algorithm with making predictions, and we want the error on those predictions to be very low. Either that error is going to be a regression error, so it's sort of like a mean squared error, it's a continuous outcome, or it's going to be, a classification error. Can I predict the right class every time? But those are questions such as when, which, and how much. When is something going to happen? We can predict a point estimate for that. Which of the things is going to happen? We're going to classify that, and how much, which is like a regression task. In contrast, parameter estimation, which is what we're going to do for causal inference, is concerned with, quote, estimating the Greeks. Greek letters are often used for the estimans that you specify, like a particular causal effect, or even a simple average. So when we're estimating a particular parameter, that parameter is just a function of the observed data distribution. And we can use machine learning for that. We wouldn't necessarily use machine learning to estimate an average, to estimate the expected value of some variable. But it's also worth noting that there's much overlap between these two tasks. For instance, let's say my Greek letter, my estimand, is actually the beta coefficient in a linear model. I may still use ordinary least squares to fit that model, which is almost like a predictive task. I'm minimizing the error in that model. And yet what I get out is actually a parameter estimate, which is the beta coefficient. So there's a lot of overlap. Sometimes I can use a predictive model to get a parameter estimate. And indeed, that's actually what we're going to be doing for plug-in estimation with machine learning. And we're going to be following the same technique that we've already seen, whereby we train the model on a data set, and then we create new versions of that data set, which we have intervened on. We, for instance, set the treatment all to 1, set the treatment all to 0, and we've generated predictions on both of those interventional data sets. And so there we've got a predictive model that's been trained for prediction, but we're using it to estimate a parameter. So there's a lot of overlap. We may be always, for instance, using predictive models, even when our underlying goal is, or the subsequent goal is actually to do parameter estimation. But the choice between whether we use linear regression or machine learning is not about a choice between prediction and estimation, because we can use both for prediction and we can use both for parameter estimation. Really, the difference between whether we choose a linear regression or a fancy machine learning algorithm should be dictated by our knowledge about the underlying functions being modeled. If we know that the underlying function is linear, use a linear regression, that's fine. If we don't know that it's linear and we don't have any idea what it is, we should be using machine learning. And sometimes it feels like the choice is actually a choice between prediction versus parameter estimation, because with linear regression, you get these parameters out for free. But no, it's still a predictive model at the end of the day. It can also just give us these coefficients if our causal assumptions are fulfilled. But the same is true for machine learning. So we don't get these free coefficients, but we fit it as a predictive model, and then we can use it to derive parameter estimates. So make sure when you're choosing between these two, it isn't a choice about prediction versus estimation. It's a choice about the underlying functions. So even if you're doing a predictive task, you may use either one. Is a linear regression going to work for your predictive task? If yes, then great. If you're doing parameter estimation, then again, it's a choice about the functions underlying the data. Okay, this is all the things I've just said. So here, maybe it's worth taking a minute to think about your own goals, particularly if you're at the beginning of your research and it's sort of still evolving and it's still in its early stages. You may be wanting to do a lot of exploratory work. And if you're doing a lot of exploratory work, you may still be more inclined to go down a predictive route in order to explore the sort of relationships in the data. You could still at the same time do estimation, but maybe you're not really clear on what the causal structure is. And like we said in previous lectures, it's very important to know the causal structure before you do parameter estimation or causal inference, because if you don't have a good idea of that structure, then you could easily end up with something that's not very meaningful. And also bear in mind, you could do all of these things sort of together in an iterative sense. That's that triangulation approach to make sure, your predictive approach is sort of consistent with what you find for the parameter estimation and so on. And also note that even if you only want to do prediction, causality can nonetheless help you with model robustness and generalizability. So here your proto-theory can inform your prediction. Your theory can also inform your prediction because you might want to use, say, only causal variables to predict some outcome. And if you do that, you'll find your model tends to generalize better to new situations. There was a great talk at University of Lausanne recently by Tom Buchler, who's a professor at University of Lausanne, who studies atmospheric sciences. And if I don't completely butcher the topic of his talk, it concerned the prediction of the evolution of storms and weather systems in different areas of the globe. And what his team found is that when they trained on all of the data, they got good prediction locally, but when they tried to generalize that model to new climates, the model just didn't do well at all. And in order to improve that, they used a causal discovery algorithm in order to restrict the set of predictors to a set of predictors that were sort of causally proximal to the outcomes that they were predicting. And when they generalized that model, it performed much better. So prediction and causality still go hand in hand. In fact, that was the topic of my machine learning or engineering PhD thesis, about how we can still leverage causality, and it's very worthwhile doing so, even if we're just concerned with predictive and utilitarian tasks like predicting something, automating a process, and so on. We can improve the performance, the robustness, and the generalizability of those algorithms if we still consider causality. But anyway, something for you to think about. So here I've just tried to demonstrate that, again, that similar graph that we saw before, that the new data test points after we've trained our model on an original set of data, when we give it some new data, those new data could either be in the extrapolation range here, or they could be in the interpolation range here. And in order to identify an algorithm that sort of works, not just well on the training data, but well on new data as well, we need to have a separation of two data sets. We need to be able to assess our algorithms on more than just the training set, because actually, if we have a very flexible function with high variance, we could actually fit a function that achieves sort of zero mean squared error. And it is absolutely possible to do that. Certainly, say with a decision tree, I think we've even got an example coming up where if the decision tree is allowed to, it will fit every single data point in your training set. But of course, that makes it a very sort of a very vulnerable or very fragile function, because if we get in a new data set, which doesn't look like the one that we've seen, even when it's in the interpolation range, the error in the test set will be extremely high. So we really need to be able to select algorithms that give us optimal fit. And in order to do that, there are a number of train, test, and validation splitting techniques. And it's a really important thing. There's a famous result in psychology by John Gottman, which concerns the prediction of divorce. I can't remember the exact percentage, but I believe him and his team managed to predict divorce with upwards of 80 or 90% accuracy. And they used a relatively flexible model. From memory, if I get this wrong, I apologize. It was some kind of dynamic model, but this model was never cross-validated. That's what I understand to be the situation in the literature. And there's this paper here that goes through exactly why it's very important to do cross-validation. And as I mentioned before, we can fit the data with 0% error if we wish, if we use a powerful enough model. So it's really important to check that model also generalizes to new data. Otherwise, all we've got is a model that works fantastically well on data that we already have the solutions for. We already have the predictions. We have the outcomes, rather. We don't need the predictions for data for which we already have the outcomes. What we care about is having an algorithm that can make predictions on new data. And if we haven't cross-validated that model, that's when we run into real difficulties. So I encourage a reading of this paper to get familiar with what happens if we don't cross-validate and how easy it is to overfit to our training data. So to detect these problems and to make sure that we can select an algorithm which performs not just well on the training data, but also well on new data, we can use various data splitting techniques. So the first one, and I'll go through each of these in turn, is a simple train test split. So we have our whole data set and we split it into two chunks, for instance, 60% for training, 40% for testing. And it doesn't have to be 60-40. In fact, that consideration depends on how much data you have. For instance, if you have a huge data set, you may be able to use, say, 90% for training and only 10% for testing. The point is that we're going to be using the testing set to make a judgment about how well our algorithm generalizes to new data. So if you have a very, very very small percentage here, then our estimate for that, what's called the empirical risk, will be quite noisy. It would be high variance. And so we want a reasonable amount of data to make the estimate of the performance. There's also train validation in tests. So this is very similar. We just do two splits at that stage. We split the data, for instance, into 60% for training, 20% for validation, and 20% for testing. I'll talk about why validation is important. In fact, it comes down to the fact that we don't really want to use this testing for any type of model decision process or for instance, the reason why we want a test set in the first place is because our model can make decisions that maximize its performance on the training set that doesn't generalize to new data. And so our test set is there to be sort of the sort of independent test set that we can sort of trust to give us a reliable estimate of its performance on new data. But if we use that test set to then tell us, oh, we should use a different model and maximize the test set, all we've done is we've just got a new training set essentially. So it doesn't help us if we want to make model decisions about which one we should use, which algorithm we should choose. And so having an extra validation split allows us to do sort of this inner loop where we go through a train and validation loop where we use their validation to pick the best model. And then once we've picked the best model on the validation set, then we can finally test it on the test set, which will give us an idea of how well that best model performs on new data. We'll talk about how the trouble with this is that it's quite wasteful of data. So we want to use maybe another technique to make the most of our data. You know, if we have 100 data points, we've now only got 60 for training, 20 for validation, and 20 for testing. So in order to make more of our data, there are other splitting schemes, for instance, k-fold cross-validation, leave one out cross-validation, and then nested cross-validation. And so I'm going to talk about these in turn. So let's see how we can even just do a simple train test split to try and understand whether our model is overfitting or underfitting the data. As I said, with the train test split, we take our whole data set and we split it into two chunks. It could be 70-30%, it could be 60-40% as we've got here. But the idea is that we have training data, which we use to fit the algorithm. There, the algorithm tries to maximize its performance, predicting some outcome, and it adjusts its parameters until it achieves the best performance that it can at predicting that outcome. And then we evaluate it on new data. We give it some new input predictors, and we ask it to predict the outcome. And if it does a good job, then we say, well, it's going to generalize well to other new data as well. And as to note here, just to reinforce that point, test data should not be used for any decision which concerns the choice for the settings of the algorithm or the algorithm that you're using. This has really got to be kept as the sort of final evaluator for that model. And indeed, if you look at machine learning challenges online, you won't get access to the test data. So they don't let you cheat. You get a set of data that you can train, validate, and test on yourself. But then when you submit your predictions for the test data, you're not allowed to see how that performs. Only they can see how your model performs. So what do? We can compare the training performance versus the testing performance, and we can see how they compare. So let's say the true function is this sort of solid green smooth curve here. And let's say we fit this machine learning function. It's kind of clear that this has got a high variance and it's probably fitting a lot of the noise in the data. And so when we see that, what we usually end up with is very good performance on the training set because it's fitting all the noise in the data, thereby reducing the error. But when we give it new test data, it does really badly because actually this isn't the underlying function. And say in this area here, it will predict a very high value when actually on average, the values will be still around this line here. So it's fit a particular example in the training set that is not reproduced in the test set. So it's not done a good job at approximating the expectation of y given x. It started to fit the noise in the data as well. So when we compare the training performance and we see good training performance and bad test performance, that's indicative that your model has overfit the data. And in contrast, if you fit a straight line to these data when it's actually a curvy linear response, then you'll get both poor or okay training performance and okay or poor test performance. And so by comparing the training and testing performance, we can get an idea for whether or not our algorithm is too flexible or not flexible enough. Is it high in bias or is it high in variance? So I want to walk through some code for doing this yourself. These are some useful libraries. I believe Party is for decision trees, random forest for random forest. Carrot or Carre, I'm not sure how it's pronounced, is a large machine learning package for R, which has lots of different functions in. And Tidyverse is also a sort of very arguably bloated package for lots of data processing and wrangling techniques. And so what I'm going to do is I'm going to generate some data, and these data actually follow an example we saw early on in the course, where we just generate some random noise for each of the nodes in a graph, and I generate some data according to an underlying structure, and I've set the outcome here to be actually math score. It was math score in the original example. It doesn't really matter what these data are at this stage, but I've created them and I've stored them in a data frame. And in order to do the train test split, I'm going to use just really this function sample, which is a very useful thing. So sample will generate us numbers between between 1 and some maximum that we specify. The maximum that we specify is here, which is the number of rows in the data set. And then I'm going to say how many random numbers that we want from between 1 and the top and the number of rows in our data. And that's going to be set to be 60% of the number of rows in the data. Now I've got this round function here just to make sure we're not generating 1.5 numbers. It doesn't make sense, just to make sure we have actually 60% of in terms of real integers, in terms of the number of values that we have. And this is just going to give us this in-train value, which is just a list of integers, a list of row numbers, basically. It's going to give us 60% of the total number of rows in the data set. And we're going to use that to index the data. So our training set is going to be the data indexed by this in-train, these in-train indices. And then the test split is just going to be the data indexed by minus in-train, these indices. So everything else apart from those indices. So this is the train test split. It's very simple. That's all you need to do to split it into 60 and 40%. And we then have this random forest. We use the shorthand notation here to specify everything except the outcome as predictors, and the outcome as the outcome here. This little full stop here, the period, indicates that we're just including all the other predictors. So if you have a large data set, you don't have to specify every single one, like x1 plus x2 plus x3, all the way up to xk, however many predictors you have. We specify the training data here, and these are a couple of hyperparameters you don't have to worry about for now. And once I've trained that model in this stage here, it will do it for me on these training data. I'm then going to generate some predictions so that I can evaluate the performance of that random forest. So for that, I'm going to use the predict function. We've seen that before. We pass in the model that we're trying to use to generate these predictions, which is the random forest we just trained, and then we give it some data. So it's going to pull in the predictors, and it's going to generate some predictions of the outcome. So the new data we're giving it here is first the training split, which is already seen to train the model on. So we generate the predictions for training, and then the predictions for test is just using the test split here. So we have now two sets of predictors, and we can evaluate how well these predictions match the true values. And so I'm going to use the mean squared error and the mean absolute error. These are two possible ways to evaluate regressors. And here, all you can see is very simply, I take the training data and I pull out the outcome variable, and I look at the difference between the outcome variable and what we've predicted for it. So the training outcome versus the predictions for that training outcome. I'm going to square it, and I'm going to take the mean. So that just follows this equation here. It's just the average, so 1 over n times the sum of everything, the average of the squared differences, which is very similar to the variance, essentially. And I'm also doing the mean absolute error, so it's essentially the same thing, but instead of taking the square of the differences, I'm just going to take the absolute value of the differences. So these are two possible metrics, and then I can compare the training performance with the test performance, and what I get is that the training mean squared error is 0.776, and the testing error is 1.084. So based on these results, we've done a bit better on the training set because a lower error is better than a higher error, and the test set is a bit higher. So that would suggest our model is slightly too flexible, that it's overfitting the data a little bit. So here is the sort of breakdown of each of these steps. And I've also put the code here in Python as well, so feel free to pause and check through that. It looks very, very similar to the code in R. The one thing that is different is the results. The random forest in the sklearn package, which is what I use here, sklearn.ensemble import random forest. This one seems to overfit the data much more than the R random forest does, and so you can see a much bigger difference between the training and the test errors here. Okay. So what do we do with these results? So we know that it performs too well on the training set and not very well on the test set. So it suggests that it's overfitting the data. What do we do with these results? Well, actually not a lot. At this stage, we can just report these results. We can't do anything with it because we can't use the test result to inform how we go about changing our performance, because we shouldn't use the test data to make decisions about the model. Nonetheless, it does provide us with an estimate of the empirical risk or the error of the model for unseen data. So arguably, if I get another data set in and I evaluate this model, the error will be somewhere around 1.084. So this 1.084 is sort of the estimate for the error on new data. So really what we need to do is consider other data splitting strategies, because we don't just want to have one model that's either good or bad and then we're stuck with it for life. We actually want to be able to use the performance that we get to actually choose the best model that we can, not just run one and then be stuck with the results. So that brings us on to the train validation and test splitting, where now we split our data into, say, 60% for training, which we use to fit the algorithm, 20% for validation, which fulfills the same sort of role as what you had in the previous case, but now we're going to use this to make algorithmic decisions. So we're going to say, oh, we're going to maybe choose a different algorithm or the same algorithm with different hyperparameters. And then once we've selected a model that we really like, then we can finally evaluate it on the test data to see, get an estimate for how that chosen model, the best model, is going to perform on new data. And make sure, again, same as before, with this test data, you don't use it for any modeling decisions. So in this case, we can use multiple machine learning algorithms. So we can fit more than one algorithm on the training set. This could be a random forest. This could be another random forest with different settings. Or this could be, a support vector regressor or something like that. So these could be different functions. And we're trying to estimate the true function here in green, this thick line. And what we see is that different algorithms sort of fit the data in different ways. We can see this algorithm here. Oh, okay, so this is probably a linear regression, because we can see that the thin dashed line here is just a straight line. And that's high bias. It doesn't fit the data well at all, but it's also not overfitting the noise. And in contrast, this thin blue line is sort of following the green line fairly well. So that looks like it's probably the best algorithm in this bunch. And then finally, the sort of thick dashed line here is high variance. It looks like it's overfitting the data, fitting some of the noise. And so here again, what we can do is, rather than considering the test data for now, we can use the validation data to evaluate these models and select the one that generalizes best to the validation data. And so we might end up with a set of results like this. We might have 3 different algorithms and then results for the training and the validation error. Now, the first thing that I would do is, if I'm presented with this big list of results, is just skip straight ahead to the validation performance, because validation performance is still an estimate of how the model's going to perform on new data. So if it does well on the validation, it's probably your best model anyway. So we go ahead to the validation and we see that, for instance, machine learning algorithm 2 gets an error of 0.65, which is the lowest error of the 3 models, 3 algorithms. And this actually, the performance on the training set is quite similar. So it looks like this is doing quite well on the training set and quite well on the test set, which suggests that it's not overfitting, that it's relatively optimal. And in contrast, machine learning algorithm 1, which is this high variance algorithm, has a really good training error. It's quite low, but it's got a quite high validation error. So that's clearly overfitting to the training set. And finally, we have ML3, which is sort of just bad on both, which is normal if you have sort of like a straight line, you fit it through a nonlinear function. So what we do at this point is we select the best model. We say, okay, well, we like ML2, this function, whatever it is. Then we're going to use that on the test set. And so we give it new data again, and we evaluate the chosen model on the test set. And now we can report the train, the validation, and the test errors all together. So it's useful to have this validation set because, again, it allows you to make model or algorithmic decisions. So how do we do the train validation split in code? It's actually very similar to the train test split. We just do the same thing, do the splitting twice. So the first thing that I'm going to do is I'm going to split it into 80-20. So even though I want 60-20-20, I'm going to first generate data that's the train and the validation data combined, and I'm going to separate out the test data. So here, for instance, I'm going to create this split first, so taking the validation and the training data together and then splitting off the test data. I'm going to do that first. And then once I've got this block of data, I'm then going to split the training data and the validation data. So here, the first is the same sampling function, sample numbers between 1 and the maximum number in your data set. And I only want 80% of the number of possible numbers in that data set. And I'm going to round it to make sure I have a whole number. So once I've got that, that's my in-train val. It's in both the training and the validation. And I can use that to split off my test data. So in this first splitting stage, I get my test data. And then in the second splitting stage, I take the train validation that combine and I just run the same thing again. But note that I have to now take, it's no longer 20% of the 100% of the data, but it's actually what's left after I now have 80%. So it's sort of like actually 70% of the 80% that's left. So if you're worried about keeping the proportions correct, just make sure that you sort of calculate this in advance. I now use 0.7 here because I'm sort of taking 70% of the 80% that's left after I've split off the test data. And then I generate the validation split. So now I have the validation split, the training split, and the test split. Now I can train 3 different models. I've got a random forest, I've got a linear model, and I've got a decision tree. Here's just talking through these steps. And I can generate predictions for each of these on the training data. I can generate predictions for all of these on the validation data. And then I can evaluate the mean squared error for each of these. So the random forest on the training data, the random forest on the validation data, then the same for the linear regressor and the decision tree. And I have a table now of results from R. And what we can see, if we just pick start with the model with the lowest validation error, we see that the linear regressor does the best. And that makes sense because actually when we generated these data, it was a linear process anyway. So it's reassuring to see that the linear regressor does the best. The performance on the training set is kind of similar. Okay, it's a bit higher, but it's not far off. And if we can contrast that with a random forest, we see that it does a lot better on the training set, a little bit higher on the validation set, so overfitting still. And then the decision tree is actually not great on either the training set or the validation set. Well, kind of similar. But again, what we would do is we just select the best model here, which would be the linear regression. Bear in mind that, of course, that depending on the size of these trained test splits, these might be quite noisy estimates. So if you run this again with a different trained test validation split, you may find that these numbers vary quite a lot. So just be aware of that. But once we've got this, then we can run it on the test set. So here I generate the test results using the linear regression, which was the best model on the validation set, and I get the result on the test set of 1.17, which is a little bit higher, possibly again just due to this random selection. There's a bit of noise in the finite samples, but anyway, that's what I would be stuck with, is this linear regression result. You can go through this loop again if you want, just so long as you're sort of not using the test data to influence your choice of the model at the validation stage, but you can go through the loop again if you need to. So just to contrast that in Python, we have the same steps here. It's all very, very similar. Feel free to pause it and look through it if you wish. And the main thing is to note these results because they look quite similar overall, except the random forest again is massively overfitting now the training set compared with the validation set. And notice that the decision tree, it has actually perfectly fit the training set. It's got a 0 error. It's fit every single data point in the training set, and it's got an extremely high validation error. So this really does demonstrate that if you have a powerful enough model, you can fit every data point in your training set. And this is why it's so important to make sure you have a separate stage here, because otherwise you'll run away with this result saying, yes, I've solved all of machine learning, when actually all you've done is you've overfit to the training data. So then we pick the best model. Again, this is the linear model. We run the test results and we find that actually slightly better on this particular split than the R example, but probably just due to random seed and the generation of random numbers. So far, a few things to notice. We've seen some differences between R and Python. This could be due to random seed. We generate the data in R and it's separate data from what we generate in Python. So that's part of the issue. But there's a clear difference in the performance of the random forest and the decision trees. And this is probably due to hyperparameters. So just to show you what these hyperparameters are, if you go to, say, the sklearn package for the random forest, this is the classifier rather than the regressor, you can see this long list of hyperparameters. So for instance, max depth, the maximum depth of the tree. If none, then the nodes are expanded until all leaves are pure. So this is a bit jargony, but if you familiarize yourself with the random forest, that will make sense. And there's lots of these different settings that you can play with, and they will all change, the degree to which you overfit or underfit your data. And there's also differences in implementation. I have found that, for instance, that in R, some of the random forests are a bit slow. That might just be due to the computational differences, but there may also be minor differences in how they've implemented, say, the bagging and the bootstrapping processes of random forest. But regardless, there are differences between R and Python, and we shouldn't expect them to give us identical results. Note that, as I've mentioned before, actually, you don't only have to have different algorithms for that validation selection. We can also have multiple copies of the same algorithm with different hyperparameters. And when we split the data, obviously we lose power because we've got less training data and we've got quite noisy estimates for the performance, for the generalization. So machine learning, if you've got really big data sets, it's not so much of an issue, but certainly for psychology, you're going to lose a lot of power. And so even though you might want a nice estimate for the performance on new data, to get a good estimate of that using the techniques I've just shown you, you need to really reduce your training set size. But note that more generally, this test and validation step is a bit like running a confirmatory study and replication. We should arguably be considering at the data collection stage how we collect more data in order to guarantee that we can still do a bit of cross-validation. It doesn't carry over quite as simply to for causal effect estimation and beta coefficient estimation, parameter estimation. There, we really want to use as much data as we can. And so there are techniques for, say, training the model using some kind of train test split. And then once we've decided on the model, fitting the model to the entire data set and then using that to estimate the causal effect. But we'll talk about that more later on. But in the meantime, how do we make better use of the data? How do we avoid losing all of this data to the test set so that we can't develop a better model at the training stage? Well, here we might consider k-fold cross-validation. This doesn't help us with making decisions about models. It can do, we'll see nested cross-validation for that, but it does help us make more use of the data. So before, for instance, we had 60% of the data for training, which is equivalent to sort of combining these 3 folds, which are just separate partitions of the whole data set. So you can see that we've split the entire data set here into 5 folds. And the idea here is with k equals 5, we have 5 different partitions of the data, and we go through a loop. We start off by using 4 out of 5 folds as the training data and the remaining fold to test the data set. So here, as we can see, we select 4 out of 5 folds, for instance, folds 2, 3, 4, and 5, to train the algorithm, and then we use, say, fold 1 to store test predictions. So we evaluate the model on this final fold. And so already we're using 80% of the data to train the model, and we're not even testing the model yet. We're just generating predictions, and we're going to store them. We go through the loop, we use another set, we train it, we have a fresh algorithm, we reset the algorithm, and we train a new one on folds, say, 1, 2, 3, and 4, and then we use fold 5 to generate predictions. We're still not evaluating the model yet. And then we keep going through this loop until we've used all the folds as test folds. So we use 4 out of 5, and then we shuffle, start again, and generate test predictions in each case. At the end of all of this, so this is another way of visualizing it. So we use all of 2, 3, 4, 5 to train, generate predictions on test fold 1, 1, 3, 4, 5 to train, generate test predictions on fold 2, and so on. Then we end up with a full data set's worth of predictions. So now we can estimate the performance of this model on the full data set. And so that gives us a much better estimation of the error for new data, but it also enables us to use a higher percentage of the data for training. Even though each model is new for each of these iterations, we're sort of using this process to establish what the performance of that model could be in the ideal world. To do this in code, it's a little bit more complicated. So let's say we still have 5, k equals 5. We can do more splits if we want. And what we do is we create a new column in the data set. So here we're taking our original data set and we're essentially introducing a new column. And that new column will contain samples, so random numbers between 1 and k, so 1 and 5. And the number of these samples, these random numbers between 1 and 5, is going to be equal to the number of rows in the data set. So essentially, for every row in our data set, we're going to have, say, a 1, a 3, a 5, a 5, a 4, a 3, a 1, 2, and so on, just randomly selecting a number between 1 and 5. And that's basically going to assign that row to a particular fold in this k-fold cross-validation process. Then what we're going to do is create a function here. So this is like an abstraction. If we use this function here, it's like saying, well, don't run this function, just define it at this stage. And this function is going to take an input, and the input is going to be the current fold. This is actually going to be the current test fold. So we might feed it, say, a 1, and that means that it's going to use all the other folds as training data and fold 1 as the test data. We're also going to pass it the data, and then it's going to split it into sort of a train and test split like we had before. But the data in the train is going to be determined, as I said, by all of the rows in the data set which have a fold number not equal to the current fold. So that's what this not equal to the current fold means. And we're also just going to separate out the column in that data which has the fold number in, because we don't need that for prediction. So this here just takes all the columns in the data except for the last one, which we assigned here to be the fold number. And for the testing set, it's exactly the same process, but now I set the rows that I extract from this data set as to be equal to the rows with the fold number assigned to the current test fold. So our train and test data are sort of split here. Then we train our algorithm as before on the training data. We generate predictions using the test data. And then we return these test predictions here. So that's all that's sort of going on in this function. It takes data in as well as a test fold. It splits it into the training folds, which is all but the current test fold. The test fold is just the test fold. It excludes the final column, which was just the name of the fold, the number of the fold for each row number in the data set. We train the random forest, we generate predictions, and we store them and return them through the function. But this, as I said, is just a function. It's not doing anything right now, so we have to call that function. So what we do, here's the annotations. This function here only undertakes sort of one round of the k-fold process. It takes in the current test fold and the rest of the folds, and then it does the training and the testing, or the generation of the predictions. We want to now iterate through all possible folds, and if k is very high, we obviously don't want to write that out each time. So we need to actually have a for loop here. So a for loop is a sort of another object in R that allows us to generate numbers sort of sequentially, or do something again and again iteratively. So what we're going to say is for current fold in the concatenation of 1, 2, 3, 4, and 5. So this is going to generate numbers starting with 1, then 2, then 3, then 4, and 5, and that it's going to call those numbers current fold. And we can pass that current fold one after another to our cross-validation function, which we defined in the previous slide. And the results, we're just going to row bind what we had already, which starts off empty, with the new result that we get from this cross-validation loop. So this is just essentially stacking the predictions as we go through each fold. Each test fold is just stacking those predictions one after another, so that we end up with a results data frame comprising all of the test fold predictions. Finally, we can use those test fold predictions to evaluate the model, and we use essentially the whole data set for this. And this is the mean squared error here, the difference between the results, the predictions from the results, and the true values. We square that difference and take the mean. So this is the process. We need the the cross-validation function defined, then we use a for loop to sort of iterate through each test fold. A variation on this is the leave one out cross-validation scheme, which is exactly the same as cross-validation, but now the number of folds is equal to the number of data points. And this is a great way to make as much as possible out of the data set you have. So if you have 100 data points, you use 99 of them to train your model, and then you generate predictions on the 100th. And then you do it again, and you do that 100 times until you've used every single data point once as a test fold, essentially. But it's only one in size. You end up with, like the k-fold process, a set of test predictions, which is the same size as the full data set. But you've also used for each of those predictions almost all the data, all but one data point. It can be quite time consuming because you end up training and testing n models, fair enough, but it does make the most of your data, as I say, and it also makes the most of testing, so you get a nice estimation of the generalization of that model. Now, one thing we haven't talked about is nested k-fold validation. So the trouble with k-fold CV and loose CV is that they don't help us with the model selection process. They just help us train the model on as much data as possible and test the model on all the data that we have. So that doesn't help us when we get our result, what to do with that result, because we can't use that result to inform us about the modeling decisions unless we have another test split. So one thing you can do is actually just to split it into train and test, and use, say, leave one out cross-validation on the training set, and then just use the test set as normal. That's perfectly valid. You can do that. Arguably, that's the simplest solution to this problem. But otherwise, you can also use nested k-fold validation, where you actually have two levels of cross-validation. You split the data into sort of train and test, and then your training set you split again into train and test. And in both cases, you do sort of an iterative loop of k-fold. So for instance, the outer loop, we take the full data set here. And in the first loop, we take, say, folds 1, 2, 3, and 4 as training set and reserve 5 for a test set. And we take this first sort of batch of folds, and then we split it again into a second level of cross-validation. So we take N1, N2, N3, N4 as training data, and then N5 as validation data. So we can use these validation results in this inner loop to get results for multiple algorithms. And then we can select the algorithm that has the best performance and test it on this held out fold 5 over here. So essentially this is extremely time consuming because now we have 2 levels of cross validation. For every iteration of the outer cross validation loop, we have all the iterations of the inner cross validation loop. And so it's very time consuming. You can set different values of K for the outer and inner loop if you want. You could have, say, many more outer loop in general than inner loop if you wish. But nonetheless, it gives you a way to actually do automatic model selection within the cross-validation, the K-fold cross-validation framework. So very computationally expensive because we essentially have K1, the outer number of folds, times K2, the inner number of folds, times M, where M is the number of models. So for instance, if we have 10 outer folds and 4 inner folds and 10 models, this is 400 algorithms that must be trained and evaluated. So it also gives you a different model for each of the outer folds, which is kind of annoying because it doesn't tell you which is best on the whole data set, but you could arguably look at what has the best average performance across everything. But it does give you a nice hyperparameter search opportunity. But maybe the easier way to do that is to say use this sort of cross-validation scheme, but instead of using all your data splitting all your data into these 5 folds, you still reserve a test data. So you can use this as a sort of validation step. But anyway, so there are a number of, I've just talked through a number of sort of train test splitting techniques. And so that'll help you avoid, overfitting or underfitting. It will help you diagnose whether you are overfitting or underfitting, and it should help you evaluate your model fairly so that you're not cheating. And also it enables you to do model selection and hyperparameter selection as well. As a quick note, I'm just assuming you're working with regular, identically and independently distributed data. That is to say that your data all is regular sort of tabular data, very simple setup. If you have dyadic data from, say, romantic partners or time series data, you have to have other considerations, which I'm not going into in this course, but it is certainly worth taking pause and making sure you have taken a course in that sort of thing before you use those data with machine learning applications, because there are certainly some different considerations that need to be made. I want to also talk about machine learning ensembles as one way to get around this hyperparameter issue. So, why do we want to necessarily just pick one model, even if we have 10 possible models and we select the one that has the best validation performance? Why don't we just use all of them at the same time? So this can also help us with hyperparameter searching, because we don't have to necessarily find a particular combination of models that gives us the best results, but we can just chuck a whole load of models together and somehow combine the predictions from all of those models. So for instance, it might look like this. We train a linear regressor, a random forest, another random forest with a different selection of hyperparameters, and a neural network. We train all these models. We generate predictions y hat 1 through to y hat k, where there are k different algorithms, and then we combine those in some way, those predictions in some way. And so we combine these in some way to get a final set of y hat, final predictions that sort of use all of the individual sets of predictions from these algorithms. And we can combine these predictions in different ways. We can use a simple average. We just average the predictions to get the average predictions, say, for y, as in like on a row-wise basis. So if we have the random forest and the neural network, we take their predictions for row 1 and we average them. We take the predictions for row 2 and we average them, and we end up with separate overall predictions. We can take a weighted average, a majority vote, and so on. And there are different ways to sort of get at some kind of consensus amongst these predictions. And one way is this sort of meta-learner approach, which is to say we can actually fit another machine learning algorithm, or it could just be a linear regression on top of these outcomes. So we treat these as variables in a data set, a sort of second meta data set, and then we combine those in some way to predict the actual outcome. So there's one particular ensemble that I want to talk about, which is the superlearner. It has some very nice statistical learning properties. It gives you sort of optimality, and that's all sort of quite technical, but it's also quite intuitive as to how it works. So just as I just described, you have a whole selection of different algorithms or algorithms with different hyperparameters, and then we pass them into a linear model. And this linear model is called the meta-learner, which takes in all the individual predictions as variables, and then it learns or fits a set of weights as you would in a normal linear regression, so beta 1 up to beta k, and we constrain these coefficients to be positive. It doesn't make sense to have a negative weight on one of these, and to sum to 1. So in other words, the sum of all of these beta coefficients is 1, and none of them are negative. And the way we train this is using cross-validation. We essentially, I've got a diagram here. So we pass our data in, we split it into the different sort of train test folds as we would normally. We train each model on each of those folds as we would normally. And then we generate a set of predictions on the validation set that we have. So we have, for each of those validation blocks in this k-fold scheme, we have sets of predictions from each of these algorithms. And then what we do is, based on that validation performance, we fit a linear model to those validation performances. So we kind of create another data set of predictions, which are essentially the test set or the validation sets, which are the sort of, if we train out, if we have five-fold cross-validation, we train on 4, and then we test and generate predictions on the 5th. We do that in all possible ways for each algorithm. We have another data set here of predictions. These are our sort of y hat 1, y hat 2, all the way up to y hat k. We obviously have true results for those as well, which we can compare against. And we use the combined data here to fit a linear model where, as I said, we have constrained linear regression where all the beta coefficients sum to 1 and they're all non-zero. And then once we've got that result, those beta coefficients, I can train each candidate learner on the entire data set and then use these weights to reweight the predictions from each of these algorithms to generate my final set of predictions. And so that is the process for the superlearner. We're going to see it in action in the next lecture. Okay, so that's it for now. I look forward to seeing you in the next talk.